Hi guys, so in the last lecture I introduced about the topic of angular momentum, which is L equals I omega and its derivation. Now I'm going to show you as to how the angular momentum is conserved within the system. Alright, now you may have heard about the conservation of mechanical energy, conservation of any type of energy in the course of mechanics. And this is also mechanics in the course of linear motion. Now take an object like this. Of mass L, velocity v, I, and mass the same mass M. Right? Velocity vf. If the force acting on the object is 0, then Vi equals to Vf. So Vi equals to the object using constant velocity. Similarly, if an object in circular motion has velocity omega 1 and another velocity omega 2, so this is at t equals t1, this is at t equals t2, right? So if the net force acting on this object is 0, then angular momentum at position, this one, this one is A and this one is B, LA is equal to the net force. I'll decide a special term for that. I'll say it as tau q, which I will introduce shortly. If the net tau q or the net force, which is the net force in translational motion is named as the tau q in rotational motion. If the net tau q of an net tau q acting on an object is 0, then the mass, the angular momentum of that object is conserved. So the LA equals LB. So IA omega A equals IB omega B. Right? So if the same object is used, the velocities are also equal, but if different objects. Say you had an object like this, an inclined plane, IA and omega A, and if some mass was dropped, see this I is equals K, and the momentum was, the angular velocity was changed to omega B. Since there was no frictional forces, and I will consider V equals 0, no friction, and no friction between this surface and this surface as well. So since there was no frictional forces, there are no forces acting. Only you can consider the impulsive force, but the impulsive force is within a very short time and does not affect the overall course of the object's motion. So there was no force acting on the system, so the momentum is conserved. So I can write IA times omega A at this instance is equal to IB times omega B. So it's very useful for objects in which we add the mass or in which we take off the mass, and we can find the final velocity of the object omega B by just saying IA times omega is E divided by IB. Right? So that's a simple calculation, which I'll use some examples to elaborate that in the next few lectures. And so that's the conservation of linear momentum. So I mentioned about the tau q. So tau q of an object in rotational motion is a multiplication of this force times the distance from its axis of rotation. this is the axis of rotation. Axis of rotation. And if this is the force, this is R, tau equals, so tau is the tau q, is the analogy of force in rotation motion. F is the force, this is in translation motion, R is the distance between the axis of rotation and the object. Take this as n. Similarly, tau equals Fr, right? F equals ma, m, I'll take R here and A here. You know A equals AR alpha. Derive that. So A equals R alpha. So this is mR squared alpha. So take this on the side. So tau equals FR, which is also equal to alpha. So this is very important. So tau equals Fr and tau equals I alpha. This is very important if you are studying about the net tau q, and also if you are taking about the acceleration of an object due to some tau q on that object. So in this lecture we discuss about the concept of tau q and the angular conservation of angular momentum, and in the next lecture we'll talk about the angular kinetic energy and work and energy, work and the power that is used in rotational motion. See you later.